Hello everyone, I hope everyone doing good and enjoyed the hidden physics of sound part 1. If anybody missed the video, don't worry, the link is in bio. You can go through it. So without let we start the hidden physics of sound. So far we have learned that sound born from vibrations. But here is an interesting question. Do all vibrations last forever? Imagine plucking a guitar string. At first, it vibrates strongly and produces a loud sound. After few seconds, the sound slowly disappears. Why? If a body has to become vibrate after giving the force, so once the body go vibrate too, and once again it has to come to the pro. But what happened to the middle, which is we call it as the mean position? So here once vibrated, when we are giving the force to it, so but the restoring force which is there, that will be trying to take into the mean position. But the restoring, due to this restoring force, once again it will be come back to the extreme position. So like this the vibration will be continued. But generally some other forces are also acting on the body so that the vibration will not last for the long time. So that's why it loses the energy. Imagine if the vibration keep going on without losing any energy. That means no external force is acting on it. Just one disturbance, it will create the continuous vibrations where the amplitude remain constant. If you see that amplitude remains constant, then that vibration we call it as the free vibration, or we can say it is natural vibration. But it will be only occurred in vacuum. There only no friction can steal the energy. But in the real life, the amplitude of the vibration will loses continuously and become at zero at the particular point. Why? Because air friction and air resistance gradually steals the energy. That is the reason if you see the amplitude will be decreasing and at a particular point it will become zero. This is what we call it as the damped vibration. Here we can say that when we are in a swing, just giving one push, after some time it is going to be stopped. But I want to continue to swing, suppose, then we have to give some external periodic force so that the vibration will be continued. So this is what we call it as a forced vibration. Now here is where things become truly magic. What happens if that outside force is given at exactly the perfect timing? Let us find out. Have you ever seen someone push a child on a swing? If you push randomly, the swing oddly moves. But if you push at exactly the right moment, the swing goes higher and higher without using much extra force. So this amazing phenomenon is called resonance. Actually, nature loves perfect timing. If your push matches the swing's natural rhythm, every push adds more energy. The swing goes higher and higher, but if your timing is wrong, you actually stop the swing from moving. A resonance works exactly the same way. When the external frequency matches the natural frequency, energy transfer becomes maximum. So that's why even a small force can create a huge vibration. So here I can say that Resonance is nothing but it is a special case of forced vibration where external periodic force frequency will be equal to the natural frequency of the vibrating body. So still you are not convinced? Let's watch some more fascinating demonstration. Here is a magic trick. Let us take two tuning forks, one tuning fork A and tuning fork B. You strike only one tuning fork, which is named as A. After a few seconds, the second tuning fork B begins vibrates by itself. Did someone touch it? No, not at all. Sound waves from the first tuning fork is transferred to the second tuning fork. Since both having the same frequency, so the resonance transfers the energy. So it's just like two friends dancing perfectly to the same beat. Now watch another surprising experiment. Here different pendulums A, B, C, D are connected to a rubber string, whereas A and B are having the same length, whereas C and D are having the different length. Initially, when I am giving the force to the pendulum A, it starts displaced. So the swing will be maximum. So due to the force transformation, that is a forced vibration, so here after some time the B also starts vibrating with the maximum amplitude, whereas C and D is not able to vibrate as compared to the B, because here the energy is slightly transferred to C and D because they are in different length as compared to the A, whereas if you see the B will are having the same length, so that is the reason the energy easily transferred. So both are vibrating with the same frequency. Resonance can be both helpful and dangerous, just like a fire. Use it wisely and become your best friend. Use it carelessly and it becomes dangerous. In musical instruments, the resonance amplifies sound and makes music richer and louder. But if resonance occurs in structures like bridges or the buildings, the resultant can be dangerous. A famous example is soldiers being ordered not to march in step while crossing suspension bridge. Why? Because synchronized marching can create vibrations that match the frequency of the bridge, causing dangerous oscillations. So this is why engineers carefully study resonance before designing the structures. This is not only the example, another example we are using in the medicine also. The doctors use this resonance in MRI machines, whereas for the communication purpose also, that is the radio stations usually they tune for natural frequency of the internal electronic circuit so that they resonate with the specific invisible radio waves already broadcasting through the air around you. And one more example, when the accelerating a random plastic panel in your car might suddenly rattle violently, then instantly stops as you speed up. The engine's RPM temporarily hits the exact natural frequency of this specific loose panel, forcing into the resonance. That's why it stopped rattling violently. Until now, we have studied sound as a physical phenomenon. But how do we actually hear it? When sound waves enter the ear, they travel through ear canal and make the eardrum vibrate. These vibrations are amplified by tiny bones inside the ear. Finally, the vibrations reach the inner ear where special cells convert them into electrical signals. These signals travel to the brain and only the do we experience sound. In other words, hearing does not happen in ears alone, it happens in the brain. Why does a whisper sound soft while a shout sound louder? The answer lies in amplitude. Amplitude tells us how much energy a sound wave carries. Large amplitude means louder sound, smaller amplitude means softer sound. Think about dropping a small pebble into water versus throwing a large stone. If it is a small pebble, then it is a sound which is produced very soft note, and that is the amplitude is very small. Whereas when you throwing a stone into the water, the amplitude is very large as compared to the soft sound, which means it gives more energy, it gives very less energy. When you come to the intensity of the sound, what is the meaning of intensity of the sound? So intensity is the energy per unit time passing perpendicularly to a given area. So once again, it is the energy per unit time passing through a given area that is perpendicularly. So that's why we call it as a intensity. So intensity have the unit of watt per meter square. Intensity have the unit of watt per meter square. So intensities also depends upon the amplitude. More the amplitude, more the intensity. When you come to the relationship between loudness and the intensity is L is equal to K log I, and this relation we called as Weber-Frencher's law, and which is we can measure the loudness by using this, and the SI unit of the loudness is decibel, and normally the conversation what we are having, that is having the 50 decibel, anything about 120 decibel causes pain and it is very considerable noise. As we know that the loudness of the sound can be measured in decibel. So the loudness is depending upon amplitude of the sound, that is directly proportional to A square. That means more the amplitude, louder the sound. And here one more thing, the amplitude of the soft sound, if you see, the very less, and whereas the loudness has been more as compared to the soft sound. And here the scale indicates of different levels of decibels, which may helpful for us and whereas dangerous to our ears also. So the maximum decibel what we can hear, that is 50 decibel is the normal conversation, which is given here, which is 50 decibel is the normal conversation, whereas if you see the soft whispering sound which is done in the libraries mostly, that is 30 decibel, and dropping a pin, that is 0 decibel. Whereas when you stuck in the traffic, that is 80 decibel, and very loud sounds like jet engines, it is about 120 decibel. So exposing to extremely loud sound for a long period can damage hearing. That's why protecting our ear is very important. Now let us answer another question. Why does a flute sound different from a drum? The answer is pitch or shrillness of the sound. Pitch depends on frequency. Higher frequency means higher pitch, lower frequency means lower pitch. Think of a hummingbird's wings moving rapidly compared to the slow flapping of a large bird. Faster vibration produces higher pitch sound. This is why children's voice are generally higher in pitch than the adult voice, whereas similarly we can see the girls have the higher pitch than that of the boys too. How we can identify the sound? For example, voice of your mother, the ringtone of your phone, and the wake up alarm, somebody calling your name. All of this, how we can identify. That is simple. We have to use the three properties of the sound. That is, one we already discussed, that is loudness, which is directly proportional to the amplitude. More the amplitude, higher will be the sound, right? And next one, pitch. Pitch already we know that is frequency. So more the frequency, high will be the pitch. If you see this note, they have a high frequency in sense high pitch. When you come to the next property, that is quality or timbre. What is meaning of the quality? So quality of timbre helps us distinguish between sounds even when they are having the same loudness and pitch. If you observe the two diagrams here, one is formed due to the tuning fork, another one is formed with the piano. Here if you see both are having the same frequency and same pitch, but here the condition is the waveforms are different. When you see the tuning fork waveforms, simply a single wave which is coming up and down, it is vibrating, very simple one. When you come to the piano, here if you see the piano, the waves are moving something differently, isn't it? So some are different waves we can see in this piano. Why it is happening like this? So the waves which are forming at here, if you see this waves which are forming at here, this is what we call it as the secondary vibrations. The waves which are representing this one, we call it as the secondary vibrations. And combiningly, and the waves which this one we call it as the primary vibrations or the principal vibration. And these all will combine to form a single principal note, which creates entirely unique waveform shape. So this is why you can instantly identify your mother's voice over your phone call. All sounds which produce the sensation of hearing can be divided into two categories. One is music, another one is noise. One music, another one is noise. Well, let us come to discuss about the music. Music is a pleasant, continuous and uniform sound produced by a regular and periodic vibrations. For example, the sound produced by a violin, piano, flute, tuning fork, etc. are musical sounds. So the sound level of these musical sounds is very usually between 10 decibel to 30 decibel. When we come to the noise, the sound other than the music sound is called as noise. It is the sound produced by an irregular succession of disturbance. It is usually a discontinuous sound. It is discordant and unpleasant to hear. For example, the sound produced when a stone is throwing on a tin shade is a noise. Usually all the sounds of levels above 120 decibel are termed as noise. Now let us connect everything we have. Vibration creates sound. Sound travels as waves. Resonance amplifies vibrations. Our ears receive those vibrations. Our brain interprets them as meaningful sounds. From a ringing bell to a beautiful song, every sound follows the same fundamental laws of physics. So the world around us is truly a giant symphony of vibration. Take a moment and think about your day. The alarm clock that wakes you up, the voice of your friend, the ringtone of your phone, the sound of rain on a rooftop. Every one of these sounds is a story written by the vibration and waves. Physics is not just hidden in your textbook. It surrounds us every second of every day. Let us quickly summarize our journey. We learned how vibrations create sound, how sound travels through the different media, why echoes occur, how resonance works, how our ear detects sound, and how loudness, pitch, and quality help us distinguish different sounds. Together, these concepts form a complete blueprint of sound. Let's end with a thought. Every conversation, every song, every heartbeat, every thunderclap begins with a vibration. What seems ordinary is actually a beautiful display of physics at work. Today, we didn't just learn about sound, we learned how invisible waves connect the physical world to our senses. The next time you hear music, laughter, or even the rustling of leaves, remember, physics is speaking to you. So keep observing, keep questioning, keep listening, because the universe is full of hidden lessons waiting to hear. Thank you for joining this journey into a fascinating world of sound. Until the next time, stay curious and keep smiling and keep learning. If you're enjoying this lesson, remember, physics isn't difficult when you can hear its story. Like, share, and subscribe.